Now, these ergodic theorems have conclusions of the form: as time goes to infinity, a time average converges to an expectation. Okay, this is just exactly the same thing as, see, what we said here, right? Ergodic theorem. So this is as n goes to infinity, the time average converge to an expectation. Right? Or it's more clear here. If you use function f, the time average will equals to expectation. Right? And that's exactly what we need in our MCMC. Okay. Now, why this MCMC thing is useful? Let's look at the example. Okay, how we can use the Markov chain to simulation. The idea here is to use the limiting theorem backward, in a sense, to generate random objects having a desired distribution. Okay, in other words, let me see here. Remember previously, if we have a Markov chain P, this is transition matrix, right? And we hope to find stationary distribution or limiting distribution, right? Which we call it pi. And of course, in the ergodic Markov chain, the pi is both stationary and limiting, right? So we're trying to find a pi such that pi times p equals to pi. Right, this is matrix multiplication, okay. Right? Which is easy, right? Because once you know this p, you can simply write down the equation and solve what is pi. Okay, and now in the MCMC, it's the other way around. Okay, in MCMC, that we have a target distribution, we call it pi. This is called a target distribution. Okay, we know pi, and based on this pi, we're trying to design a Markov chain. Okay, such that, so we're trying to find this p, such that this pi is the limiting distribution or the stationary distribution of this p. So you can see this is the reverse problem. Okay, and you can actually imagine that if you give p, then usually we can solve the equation, and it's easier to find a unique pi. Okay, most of the time, if it is ergodic, then you can solve it, find a unique solution. However, if you are given pi and trying to find p, then there are actually, most of the time, there are infinite possible p there. And we are actually trying to find the one that's the most useful in the MCMC. Okay, so the MCMC is just a reverse problem as the problem we learned before to find the stationary distribution. Okay, now here is the example. Generating a random, uniformly distributed 4x4 table of non-negative integers having specified row and column summations. Okay, here I give you one example. Here is a 4x4 table, and all the numbers in the table has to be non-negative. Okay, it could be 0, but it could not be negative. And those numbers, we have the specified row summation. So all this is 4x4 table has to have the first row add up to equals to this number, second row add up to equals this number. So those numbers are fixed, and the column summation are fixed. Okay, you cannot change those. And you can imagine there are a lot of 4x4 tables satisfy this condition, right? Because those column summation and the row summation are fixed, and the qualified 4x4 table are actually finite, right? You can count there are finite possible tables are there. So what we want, you can think about in this case, this is one example, right? But there are finite possible tables satisfy this condition, and we can think about this is the pool contains all the table, right? We don't know how many tables are there so far, but the number is finite, right? So this, you can think about this as sample space S contains all the tables are there, okay, and there are finite tables there. So I can, for example, I can make, there's a one table here, there's a one table here, and right, and there's a one table here. You can think about this example is just this table. Okay, this is a big pool, contains all the qualified table here, 4x4 table, and we don't know how many are there, but they clearly you can count, right? We can count it, because the row summation is fixed and column summation is fixed. Okay, so what we want is we need to sample from this S uniformly, which means equal likely, right? All the tables equal likely to be sampled from here, and how we can get the sample. For example, I want 1,000 tables as an equal likely sampled from here. How we can do that? Okay, so it's difficult because first of all, how many tables are there? We don't even know that, right? So if you think that the total number of the tables are this, the total number of S, right? Then the target, our target distribution is just uniform distribution, right? Which means that probability to sample every table is simply just 1 over the total number of S. However, because we don't know this total number of S, we don't really know exactly this value, right? Which means that we only know the target distribution is uniform, but we don't know exactly the number of this target distribution. Okay, so then you can see the problem. We don't even know the target distribution, but now we want to sample from my target distribution. Okay, how can we do that? Okay, so the way to do it is actually use MCMC, use Markov chain. Why we can use Markov chain? You can see that we know our target distribution is a uniform distribution, and we're trying to design a Markov chain. So the Markov chain is something like a x1, right? x2, x3, and so on. And each of the x is a table like this. Okay? In this Markov chain, each x is a table, it's a 4x4 table. And we can design a Markov chain so you can jump from x1 to transit from x1 to x2. x2 is another table, right? The Markov chain is actually transit from one table to another table. Okay? And if we can find such a Markov chain such that the uniform distribution is the limiting distribution and the stationary distribution, then we're done, right? We can just starting from this table and run this Markov chain long enough, and by theorem, by ergodic theorem, we can get our sample. So that's the idea.